Hello there. This is the first video in a series of videos about polynomials, and we're going to start out at the basics, what a polynomial is, and basic features of polynomials, including finding zeros and end behavior. So in this video, we're going to go through a number of different examples to give you an idea of how we might go about describing a polynomial and then eventually graphing it. So first of all, what is a polynomial? Well, if you've ever seen functions like y equals x to the fourth plus 3x squared minus 8x plus 5, this is what's called a polynomial. And basically a polynomial of degree n has this form, a sub n times x to the n plus a sub n 1 minus 1 times x to the n minus 1, and then all the way down to an x squared term, an x, and an a sub 0 term. These are what are called terms here that compose our polynomial. And so what is it? It's just a sum of our power functions that we saw in the previous video. Okay, so we got a bunch of power functions that were monomials, and now we turn them into polynomials because we have lots of different terms. So in this case, polynomials are continuous. They don't have any breaks or holes or gaps. And it's a smooth function. It doesn't have any pointed turns. So, very nice. I enjoy graphing polynomials because there's a lot of mystery to it, and you're solving this mystery to figure out what this polynomial looks like. And there's lots of different types, just like snowflakes have all kinds of different characteristics. So plotting points, intercepts, and end behavior all help us to figure out what the graph of that polynomial looks like. So let's start with end behavior. Polynomials have either even or odd end behavior based on two things. So we would look at the degree of the polynomial or at the leading coefficient. So this is altogether called the leading coefficient test. So we're going to look at basically at odd positive, odd negative, even positive, and even negative end behavior. All right, so odd positive, that would be something like x cubed minus 2x squared minus x plus 1. We look at two things, the degree of the polynomial, which is the highest power of the polynomial. All right, in this case, the degree would be 3. That's an odd number. All right, and then we look at the leading coefficient. The leading coefficient is whatever coefficient is with the highest power. In this case, that's with the x cubed. That leading coefficient is 1, which is a positive number. So we say this has odd positive end behavior. And our odd positive end behavior, it's odd because it has different behavior on different sides, but eventually our end behavior is positive. So as x goes to negative infinity, f of x goes to negative infinity. As x goes to positive infinity, f of x goes to positive infinity. So everything matches whatever x does. Odd negative, on the other hand, still has that odd degree, but it has a negative coefficient in front. All right, and so what that does is it switches our end behavior. As x goes to negative infinity, f of x goes to positive infinity. As x goes to infinity, f of x goes to negative infinity, so everything's switched. But it's still odd because you've got different things going on different sides of your end behavior. Even positive and even negative both have to do with an even degree for our polynomials. So here we have an x to the fourth and an x to the sixth. In both of these cases, the degree is an even number, right? So you get the same sort of end behavior on either side. So even positive, notice our leading coefficient is a positive 1. Right, so we end up with positive end behavior in both cases. Even negative, right, here we have a negative x to the 6 plus some other terms that are smaller. All right, and so in that case, we end up with an even negative end behavior, so f of x goes to negative infinity on both sides. And you can see, based on what we did with end behavior before, what these graphs look like based on those characteristics. Other terms that we need to know, a turning point is where a graph changes from increasing to decreasing or vice versa. We know those as relative extrema as well, and you'll learn more about that in calculus as we go along the route. For polynomial, maximum number of turning points is your degree minus 1. All right, so there's a reason for that. That'll be calculus based, but just know for right now, your maximum number of turning points is your degree minus 1. Various terminology we'll need to know. If c is an x-intercept, we also say c is a 0, and x minus c is what we call a factor. All right, so if x minus c to the m is a factor of the multiplicity, that power that we're raising our factor to is what we call the multiplicity. And it's going to help us determine what the function looks like around that 0, x equals c. All right, so let's do some examples here. So for the function f of x is equal to x minus 5 to the fourth, we're going to determine the end behavior, the zeros, and state the number of possible turning points and give a graph. So let's start with the end behavior. With end behavior, we want to always look at what the highest power is. In this case, it's going to have to do with whatever the x is doing. The 5 isn't really contributing much of anything as far as the end behavior. So we would say the highest power here would be x raised to the fourth. So our degree would be 4. If we look at our leading coefficient, it's going to be x to the fourth is our highest power. And so our leading coefficient is 1x to the fourth. So in this case, we have an even power, and our leading coefficient is a positive number. So our end behavior is positive in both directions. So our zeros, we want to set each of our factors equal to 0 and solve. So when we set x minus 5 to the fourth equal to 0, we get x is equal to 5. And that also tells us, by the way, that the multiplicity of this root is 4, because this is x minus 5 raised to the fourth power. That's going to play a key role here. Here, since the degree of the polynomial is 4, our maximum number of turning points is 4 minus 1, which is 3. Now, you don't always have that number of turning points. There are some other factors that go into this, all right? But this is going to be our maximum number of turning points. Just like our maximum number of zeros is going to be whatever our degree is for our polynomial. All right, so if you notice, all right, we said what our end behavior was. We already talked about that. Multiplicity is 4. Maximum number of turning points is 3. And now we get a graph of the polynomial. So in this case, we have 1, 0 at x is equal to 5. The multiplicity is 4. So what that really means is that around that 0, x is equal to 5, our graph looks like a fourth degree polynomial, the x to the fourth. Not really much mystery there yet, but when we see this later on, we'll see what goes on. So we have our end behavior, which rises on both sides, and we have only one turning point in this case. Remember, we said our maximum number of turning points is 3. Well, in this case, there's just one of them. All right. So example number 2, for f of x is equal to x cubed plus 12x squared plus 35x. We want to determine the end behavior using that leading term test. The zeros state the number of possible turning points, and we're going to give a graph of the polynomial. Let's start with end behavior. Highest power is x to the third, so degree is 3. Leading coefficient is 1. That's a positive number, so our end behavior matches what our x is doing. Limit as x goes to negative infinity is negative infinity. Limit as x goes to infinity of f of x is positive infinity. Now, when we go through and try to find our zeros, hopefully in algebra you learn some techniques. One technique that we can do is we can pull out an x that's in common with all of our terms here. And when we do that, we might simplify our function in a way that we can actually factor out using techniques that we know. So in this case, if we factor out an x, we're left with an x squared plus 12x plus 35. That factors into x plus 7 times x plus 5. So we have an x times an x plus 7 times an x plus 5. All right, remember, throughout all of this, you need to make sure that you're setting this function equal to 0, because that's the whole idea here. All right, when we're actually solving this, we're saying the product of 3 numbers has to be 0. Well, one of those 3 factors, I should say, is equal to 0. So when we set each factor equal to 0 to solve for possibilities, we get x equals 0, x equals negative 5, and x equals negative 7. And all of these have multiplicity 1 because they only occur one time. Finally, turning points. Our maximum number of turning points, since this is a degree 3, is 2. So if you have more than 2 turning points, you haven't drawn this correctly. So let's take a look. So just to recap, we've got our end behavior, which is negative on the left, negative infinity on the left, positive infinity on the right. The multiplicity at each of our roots is 1. Going through our roots are zeros of 0, negative 5, and negative 7. So when we pass through those points, we want to have linear type behavior, right? Because we only pass through in an x to the first type power. And our maximum number of turning points is 2. All right, and when we put it all together, we have a root at negative 7. We're going to go through the axis because we have a linear-like behavior. At x equals negative 5, we also go through the axis. And at x is equal to 0, we also go through the x-axis. All right, and our graph is going to have 2 turning points, and we match it with our end behavior here. We'll practice more of this in class, but you see how all these pieces go together to get our nice graph. Finally here, let's suppose f of x is equal to x squared times x plus 3 squared times 2x minus 1. We want to determine end behavior, state the number of possible turning points and zeros, and graph the polynomial. So end behavior, this is where you have to think a little bit here. You always have to look at what the highest powers are. If I can actually get this here. So we'll exit the drawing in this case. So our highest power is going to be x squared times x squared. That's the x plus 3 squared. The highest power there is going to be another x squared times a 2x. So in that case, I have an x squared times an x squared times a 2x. And altogether, that will mean that my highest power will be x to the 5th with a leading coefficient of 2. Okay, so our degree is 5, leading coefficient is 2. All right, so in this case, the end behavior is the same as what's happening with x. So we get limit as x goes to negative infinity is negative infinity. Limit as x goes to infinity is positive infinity. Our zeros, well, nicely, they've already actually figured out the zeros for us because we've already got this in factored form. We've got a 0 at x is equal to 0 with a multiplicity of 2. At x is equal to negative 3 with a multiplicity of 2 as well. And then if we set 2x minus 1 equal to 0, we get a root of 1/2 with multiplicity of 1. We already said the degree is 5, so the maximum number of turning points is 4. So let's take a look at what the graph looks like in this case, with all these pieces put together here. Well, we notice that our multiplicity at negative 3 was 2. So what happens is at negative 3, our graph looks like a degree 2 polynomial, a quadratic in other words. So we see it has a turning point at negative 3. We also see we have a turning point at 0. It's kind of harder to see because there's just a really small bend in the graph there, but there's a turning point at 0. And then we're going to go through the axis at 0.5. All right, so put all together, all right, we get this nice graph with 1, 2, 3, 4 turning points. All right, in summary, there's a lot of features of polynomials we'll use to help graph these polynomials. And behavior is one, zeros is another, multiplicity and turning points, and they're all going to play a major role in getting us a picture of what our polynomial looks like. Thanks for watching. We'll see you on the next video.